Very often it happens that you can find one vector space inside another vector space using the same addition and same multiplication. In this case, the smaller vector space is called a subspace of the bigger one. And subspaces are an important topic which we're going to discuss in this video. So just a bit of vocabulary first of all. When we talk about a vector space over the field F, then the word scalar just refers to an element of that field. That's because you can scalar multiply by elements of F. So the definition for a subspace is that a subspace of a vector space V is a subset U of V with certain properties. So first of all, U's got to contain the zero vector. Second, U's got to be closed under addition, which means that if you've got any two elements of U and you add them together, the result is another element of U. Finally, property 3 is closure under scalar multiplication. And what that means is that if you've got any scalar lambda and any element U in big U, then lambda times U is in big U again. And the notation that we use to say that U is a subspace of V is this. We use a less than or equal to symbol like this. So to take a couple of examples of subspaces, just to start off with, if we have V being R squared, and then I'm going to let U be the set of all vectors of the form x, 0, 4, x in R. So all the vectors whose second coordinate is 0. Then I claim that this U is a subspace of V. So in order to prove that, I've got to check the three properties. So let's just do them one by one. Well, one for sure, if we take x equal to 0, then the 0 vector 0, 0 belongs to U. So for sure, U contains the 0 vector. Property 2, we need closure under addition. So we have to take any two elements of U and prove that their sum is in U. So let's let x, 0 and y, 0 be elements of U. Any two elements of U have this form. Then their sum is x plus y, 0, and that has second coordinate 0, so it's an element of U. That means property 2 is okay. We check that the sum of any two elements of U is another element of U. And so finally, property 3, I have to do closure under scalar multiplication. So I have to choose any scalar lambda and any element of U, which I can write as x0 for some real number x. Well, then if we work out the scalar multiple, lambda times the vector x0, that is lambda x0. In particular, the second coordinate is still 0 because lambda times 0 is 0. So let's just spell that out. That's lambda x0, which is an element of U. So property 3 is true as well. If you take any element of U, you multiply it by any scalar, then the result is again an element of U. Therefore, this U is closed under scalar multiplication. Okay, so there is an example of a subspace. Let's look at an example of something which is not a subspace. So sometimes people get a bit confused when we talk about these vector spaces consisting of column vectors, like r squared or r cubed or r to the whatever. So one example is that R is not a subspace of R squared. There's a non-example for you. I mean, R is not even a subset of R squared, so it can't even get to the very first part of the definition, which talks about a subset U of V. So since R is not a subset of R squared, it cannot possibly be a subspace. Okay, so one last thing to say about this definition is that we can use the definition a lot of times. So the definition of a subspace of a vector space V is that it has to have those three properties. It's got to contain the 0 vector, it's got to be closed under addition, and it's got to be closed under scalar multiplication. So if you have a subspace U of V, and if you've got, let's say, a load of elements of U. So let's say U1 up to UN are in U for some natural number n. Then if we use, well, let's say we've got some scalars as well. So let's say lambda 1 up to lambda n are scalars. Well, we can use these vector space, these subspace definitions lots of times. So U is closed under scalar multiplication, so lambda 1 times U1 is an element of U, and lambda 2 times U2 is an element of U, and lambda 3 times U3 is an element of U, and so on. But then we also have the closure under addition property. So if lambda 1 U1 and lambda 2 U2 are both elements of U, then so is lambda 1 U1 plus lambda 2 U2. And similarly, since lambda 3 U3 is also an element, I can add that as well, and I'm still an element of U. So using the closure under addition and closure under scalar multiplication rules lots of times, any expression like lambda 1 U1 plus lambda 2 U2 and so on, plus up to lambda n UN is again an element of our subspace. In other words, subspaces are closed under taking linear combinations. So remember, we introduced this term linear combination of U1 up to UN to refer to what I've written there. So this is useful because we met the idea of linear combinations before when we were talking about doing matrix multiplication. You saw that when you multiplied a matrix into a column vector, the result was a linear combination of the columns of the matrix that you multiplied. So here is going to be a link between subspaces and doing matrix multiplication. We'll revisit this in a couple of slides. So let's take some new examples of subspaces. I want to take some examples and some non-examples, and we'll start off, well, I'm not going to tell you which one, you can work it out. So we'll let V be R squared, the vector space of all height 2 column vectors with real number entries, and let's take U to be the subset of V, which consists of all vectors with integer entries. So the question I have for you is this thing U a subspace of V? Maybe pause the video and think about it. Okay, it's certainly a subset, but is it a subspace? So does it contain the zero vector? Is it closed under addition? Is it closed under scalar multiplication? So the answer is no. Okay. It does contain the zero vector. It is a subset of V. I mean, we can get started because U really is a subspace of V, a subset of V. It does contain the zero vector because 0 is an integer. But, well, let's go one further. I mean, it is closed under addition. So if you add two elements of U, the result is another element of U. So U is closed under addition, and it contains the zero vector 0, 0, but it is not closed under scalar multiplication. So our vector space V is a real vector space. The scalars that you're allowed to multiply it by are any real number. But if you multiply it by certain real numbers, if you multiply elements of U by certain real numbers, the result will not be an element of U. So for example, root 2 is a legitimate scalar, this vector is in U, but if you do the scalar multiple, you get this. So root 2 times 1, 1 is root 2, which is not an element of U because its entries are not integers. So this is an example of something which is closed under addition and contains the 0 vector, but is not a subspace because it's not closed under scalar multiplication. So let's try another example. Let's try an example with our function space. So we'll let f be the vector space of all functions from the real numbers to the real numbers. So we define the operations on this vector space, the addition and scalar multiplication, in our vector spaces video. So we'll now let U, curly U is going to be all of the functions f in f with the property that f of 1 is equal to 0. So all the functions which are 0 when you give them the input 1. Then I claim that this U really is a subspace of f. So let's check this. We have three things to check. We've got to check it contains the 0 vector. The 0 vector in f, you'll remember, is the constant function which always has the value 0. So in particular, it's 0 or 1. And that means that the 0 vector, which is in this case the constant function which is always 0, that really does belong to U. So property 1's okay. Property 2 is closure under addition. So I have to take two elements in U and show that their sum is in U. So let's take two elements f and g be in U. Then I want to check, is f plus g an element of U again? So you'll remember the definition of f plus g was that if you evaluate f plus g, then the result is f of 1 at 1, then the result is f of 1 plus g of 1. Now here, because f and g are in U, that's 0 plus 0. So f plus g is still an element of U. Okay, so U is closed under addition, and of course it's closed under scalar multiplication for the same reason. So we'll let lambda be a scalar, and we'll let f be an element of U, and then lambda times f was defined to be the function whose value at x was lambda times f of x. So in particular, lambda times f of 1 would be lambda times f of 1, and that's lambda times 0, and now I don't care what lambda is, that answer is always 0. So lambda f is an element of U. Right, we've checked that U contains the 0 vector, it is closed under addition and closed under scalar multiplication, so it is a subspace. Okay, but let's just think about what would happen if we changed this example slightly. So what would happen if instead of putting a 0 here, I put some other number, so I put a 1? What would happen then if we looked at all the functions such that f of 1 was equal to 1? Would that be a subspace? What do you think? Maybe pause the video and think. Well, the answer in that case is it would not be a subspace. And the reason it wouldn't be a subspace, well, actually it would fail all of these, would fail all three conditions. So it wouldn't contain the 0 vector because the 0 vector doesn't send 1 to 1. And it wouldn't be closed under addition because if f of 1 is 1 and g of 1 is 1, then f plus g of 1 is not 1 but 2. And it also wouldn't be closed under scalar multiplication, so it's just hopeless. It doesn't obey any of the rules. So this would not give us 1. One final example then. Let's take a more interesting example. So what should we do? Let's take the space of all 2 by 2 matrices. So we'll let V be the space of all 2 by 2 matrices with real entries. And we're going to let U be equal to all the matrices A in V with the property that A transpose is equal to A again. So those matrices are called symmetric. A matrix is symmetric if it's equal, or if and only if it's equal to its own transpose. So then, well, you should prove that U is a subspace of V.